Right, so repeated measures designs that we're going to talk about today, and DIN projectors. Probably both those things at once. So, right. So, by way of introduction, let's say you're interested in learning or forgetting. I mean, a lot of you guys are in my memory class. We talk a lot about forgetting in that class. You know, of course, learning or memory is just the persistence of learning. So, we're going to have to look at data like this, and if we're looking at something like learning or forgetting, independent groups don't work. They can't. You can't, well, I mean, I guess in a way you could, but I can't offhand think of a way that independent groups would work here, because you'd have to test the same people over and over again to see if there's learning or to see if there's forgetting, right? I suppose we could have one group that has a 5-minute retention interval and one group that has a 20-minute retention interval for a memory test, and then call the difference between those two groups forgetting, and I guess it would be, but I'd like to see individuals' scores drop in. You know what I mean? So I think we want to test the same people over and over again. And of course, we could be doing memory experiments with, I don't know, black-capped chickadees, test the same chickadees over and over again. So we have to look at, or we're looking at change over time generally. So anything with development as well. Okay, so we're looking at change over time, and we're going to probably want to use the same participants over and over again. Now, what you end up with is this. So if let's say we want to look at 5-minute, 1 hour, and 24-hour retention intervals for remembering a list of words, which is a pretty standard kind of approach. It's the same group. So schematically it looks like this: group 1, group 1, group 1. It's the same subjects tested over and over again. Okay? The same subjects tested over and over again. So hopefully this all works out, and then everybody's happy. All right. Okay, I think the mic works. Okay. Sorry again. I think I just hit in your ear. Right. Okay. Good. Well, let's see if we can do this. So, I hope some of you have detected a potential problem. I've kind of teased the problem by constantly saying that we're going to be testing the same people over and over again. There's a problem here. The observations aren't independent. How many times, every time, have I said independence of observations is the most important, that we cannot violate that assumption, and we would be violating it. If I test Jade once and then test Jade again, there's a variable in there that's the same. It's the level of being a person that means Jade. So if that's the case, those are dependent observations. And then after that, I test Madison, and again, same thing. Oh, she's got the level of humanness called Madison. So those observations are not independent. And I keep telling you, always have independent observations. Now, obviously, we do experiments on forgetting. Obviously, we do experiments on learning. So this isn't a huge insurmountable problem, but it's something we're going to have to deal with, isn't it? Yeah, we're going to have to deal with this. Well, let's just tell the model then. So our model never has anything about repeated measures. Well, until now it will. We're just going to put it in the model. So how do we fix problems? Well, if we can, we account for them. So we're going to account for variance due to the fact that we have the same subjects tested over and over again. Okay, so that's what we're going to end up doing here. That should help us out and allow us to do such an analysis. Okay. So far, questions. Does that make sense what I just said, that how it's an issue, and you'll see in a second we fix it. Okay, good. So now our model changes a little bit. We just threw a pi in. X equals tau plus pi plus epsilon. X equals mu plus tau plus pi plus epsilon. So any score is the grand mean plus the treatment effect. This should sound incredibly familiar. Indeed, it is in fact, so far, exactly the same as the vanilla one-way analysis of variance. And error, in fact, we've only added in one new thing. So the only new thing we've added is that term, pi. I like to think that pi stands for people. Tau is for treatment, pi is for people. Yeah, so it's the effect of subjects. And I'm going to use subjects here. I'm not going to say participants. You would say subjects if you were doing this. And it wasn't a psychology class. This is actually a stats class. So we're just going to say subjects, okay? Okay, this is good. Now we're happening. So the important thing to note here is we've only added one term. This isn't going to change things a whole hell of a lot. It's going to change things some, or who we wouldn't do it. It's obviously got some purpose, but it obviously, again, isn't going to be a giant change. All right, questions so far? You good? Okay, so if you get the logic of this, I think you'll be okay. So now the design looks like this. Notice what I've done here is I've put in a new variable. I've called it subjects. I'm saying we have 4 subjects in this experiment because I made up the experiment and I said it's going to have 4. It's just I picked 4 because that's what fit on the slide. So I got 5 minutes, 1 hour, 24-hour attention intervals, and I've got subject 1, subject 2, subject 3, subject 4. And they're all tested repeatedly. Okay? Everyone's tested 3 times at 5 minutes, 1 hour, and 24 hours. So now we don't have to go out and find 12 people, we just got to find 4 people. And with the way that people having trouble getting participants this year with their honors thesis projects, maybe, it'd be great if you guys could do everybody's project. It'd be awesome. All right. So what's going to happen here is that we're going to decrease error. Well, why have we decreased error? Well, let's just take a look. Let's go to the board here. We don't do that often. But let's think about this. X equals mu plus tau plus epsilon. That's the vanilla sort of one-way analysis of variance. The one that we have is called X equals mu plus tau plus pi plus epsilon. So this, you take a look at that. That should tell you that where does the where does the pi come from? Anybody says the oven, I'm going to smack you. Because I thought it as what to say. I kid, obviously. I wouldn't hit any of you. Because I think you could probably all take me. But also I'm recording this. The worst thing, assaulting someone on, you'd be really it's like a bad idea. So many bad ideas. Let's beat somebody up and let's record it. Put it on the internet. People do that though. Anyway. It's got to come from somewhere. There's only one place it can come from. It can only come from error. Right? Because this is here, this is here. Error now splits into pi and error. Okay? Do you see that? You see, it's the only place it can come from. Remember, those are constants. Eh? Like those are Greek letters. Okay. Good. So we've decreased error. That's good because the bottom part of the analysis of variance fraction is the error. It's called the error. In fact, we call it the error term. The top part, the numerator, is now the same size, right? Because tau, it's tau plus epsilon, it's got tau. So it's the same value. What's been made smaller is epsilon. Now we've lost degrees of freedom here. We'll see that in a second. We have lost degrees of freedom. We have fewer degrees of freedom, and generally fewer degrees of freedom is bad. We like lots of degrees of freedom so the numbers can vary a lot. Okay? We don't want hardly any degrees of freedom. So we actually are paying for this, so we get a decrease in error, but there's no free lunch. You have to pay for it, and you pay for it in degrees of freedom. It's harder to... Less degrees of freedom mean a higher critical value. A higher critical value is, by definition, a little harder to exceed because it's a bigger number. But we're going to offset that, hopefully, by making error smaller. Okay? This is one of the questions on assignment 3, which is already posted. You should look at assignment 3. This is actually literally, I believe, one of the SPSS videos. Just shows you how to do it. So look at those. I think there might be a PSPP one showing you how to do it too. All right, let's take a look at this. What happens? Anyway, questions then at what I've said so far. Okay, so this is what I mean when I talk about paying for the reduction in error with the reduction in degrees of freedom. This would be the one-way analysis of variance. We would have 2 degrees of freedom for attention interval, right? We have three attention intervals. we would have a total of 11 degrees of freedom. So we would have, because we have 12 observations. And error would be 9. Now the thing is, we know that we can account for something else here. So we got a new variable called subjects we're going to bring in. And you see what's happened here? See, 3 and 6 is 9. So the degrees of freedom for subjects and error are the same as the degrees of freedom for error in the one-way analysis of variance. Degrees of freedom have variance. They travel together. So we've split the variance up just from error for one way into subjects and error. Okay? Again, you see what I've done here. Okay? Okay, so I hope this doesn't look too scary at all. This is what we've done. Okay, so let's do a thing. There we go. Okay. So any design has a finite number or amount of variation and a finite number of degrees of freedom. That's the first point there says. So it's a number it's a knowable number. We can calculate it. So that's the nice thing about it. So it's finite and knowable. It's not like it's one of those weird things that we don't know, like parameters. This is something we calculate. That's nice. So the degrees of freedom go with, we're going to partition the degrees of freedom and the variation just a little bit further. That's all we're doing here. We're just dividing it up a little bit more. So mean squared for retention interval, which we would say for mean squared treatment, would be the same for both analyses. Again, take a look at assignment 3 on the LMS, and you'll see that I actually have you do this and prove this to yourself, to do an analysis and show that they're different. They're different and the same, basically. So is the reduction in mean squared error worth the loss in degrees of freedom for error? That's the question. The answer is almost always yes. Like, unless your professor really cooks an example, and it's hard to cook an example where this doesn't work. It can happen. Okay, so in fact, one of the questions, again, on the upcoming assignment that you have is, was it worth the loss in degrees of freedom? Okay. And remember, I want you to look at it, don't just say yes or no, because as I just said, it would be certainly possible for me to cook an example where it wasn't worth it. But I can tell you also in the real world, like 95% of the time, it's totally worth doing this if you can. There's so many advantages within subjects design. Yeah, so it's almost always yes. And as I said, I can think of examples where it's no, but those examples involve me making up numbers. A high school locker room smell vibe in here today. Notice that? Just saying. I think it was an intro class here for us. That's probably why.
They had an exam.
Oh, they had an exam. That's probably what it is. You can just smell the fear, okay? You can smell the fear.
I also love that there's sand all over the floor.
That's true, eh?
But there's no sand
At the
outside.
entrance to the building is a big pile.
Maybe they came in here. Maybe Dwayne was doing something because he's teaching intro. Maybe they were doing stuff with sandcastles, playing a little bit. Maybe it was that.
She did that for all of intro.
I don't think he does that. All right. So let's think about this for a sec. Is it realistic to think this? Okay, now I want you to, this is probably the most thinking I want to get you to do so far in the course. Take a look at Arwen's just lost consciousness for a moment, but okay, is it realistic to think that this is possible? That x equals mu plus tau plus pi plus epsilon? Okay, so what I'm saying is it reasonable to say any score is the grand mean plus treatment plus the fact they're different people plus error? Okay, so if we had different, let's say we're all getting tested, all of us, and we're going to do different retention intervals. So whatever retention interval you had, and then plus the fact that it's goes plus or minus, well, whoever you are. So there's Dave, there's Arwen, and there's let's pick somebody else here that I haven't been picking on, Justin. Okay, so we're gonna that's the different levels of people. That's different levels of people. 1, 2, 3. We just used the words Dave and Justin, and did I say Arwen again? Okay. All right. Shouldn't you think, though, that pi should interact with tau? Because, I mean, let's do this again. The three of us. Are our memories exactly the same? Like, are they affected exactly the same way by all variables? That's actually an empirical question. Some people forget things more quickly than other people. Right? You guys, both you guys are like significantly younger than I am. Like almost 40 years younger than I am. So I bet your memories are better than mine. Just, decline. I'm old. Can I come too? I know people remember that Simpsons episode. So it's probably the case that there's an interaction, right? That on the other hand, I have really good memory for some things. So maybe some things, I'm better. Whatever, it doesn't make a difference. The point is, we're not all the same. There's probably an interaction going on here. So there's something other than the fact that it's Justin, Irwin, and Dave. There's the fact that Justin, Irwin, and Dave are affected differently by retention intervals. Oh, that's an interaction. There should be an interaction. There has to be an interaction here. Pretty sensitive. Or assume at least there could be, and then we can measure it. And if it's 0, who cares? So it's going to change the model. And if the model changes, it changes some other stuff. So we're just going to have to take this into account, the fact that we have tau and pi. And now the model looks like this. X equals mu plus tau plus pi plus tau pi. You ever had tau pi? They're delicious. I've been making that joke, and I kid you not, since 1995. In this exact point in this course, at that time it was at U of T, but we all, no, not 95, 92. Holy Jesus, I gotta get some new material or some writers or something. All right. So let's think about that. Let's look at that. There's something missing there, it looks like, right? So, x equals mu plus tau plus pi plus tau pi. Where's the epsilon? It's not a typo. I've forgotten it. It's just not there. Huh? Yep, there's no epsilon. We have exhausted the degrees of freedom. We've used them all up. We can't get anything else. This is going to be a pretty common thing here on in, by the way. Or common enough that there are times when there isn't something called error. We still get error terms. We can still do analysis of variance, but there isn't something just called error. So we treat S, subjects, as just another variable. Just some other variable. It doesn't matter. It doesn't matter that the levels are Arwin, Dave, and Justin. Who cares? The numbers don't know where they come from. They don't care. Okay? So what we get, in this case, for our original design would be retention interval has 2 degrees of freedom. Subjects has 3 degrees of freedom. Remember we had 4 in that experiment. And then retention interval by subject interaction has, 6 degrees of freedom. It's just an interaction. There's nothing fancy how you calculate it. And if you note that we have 11, there's no more, we only had 12 degrees of freedom. What am I going to, or 11 degrees of freedom? There's nothing left. There's nothing left. We have exhausted the degrees of freedom. Okay. Questions so far? You're a good group. You don't ask a lot of questions, or you're completely confused. It's one or the other. It's got to be. I choose to believe that I'm an amazing teacher and you're all incredibly smart. Let's go with that. How the hell is it going to work if we got no epsilon? Error term is actually a treatment by subject interaction. Subjects, there's a reason I told you about random effects and fixed effects. Subjects are a random factor. Well, they're not a fixed factor. Did we randomly choose me and Arwin and Justin? No, that was the 3 that I had. But it's closer to that, to a random effect, than it is a fixed effect. The expected values work out that we end up with something we can divide by. We don't test the subject factor. So there's nothing to, we don't take mean squared subjects and divide it by something. We're going to take mean squared retention intervals, or mean squared treatment then, and divide by the subject by retention interval interaction, or generally the tau by pi interaction. And that's going to be our F-test. We're not going to do a subject test. So we're just going to leave it there? Yeah. There's no error term for mean squared subjects. We can't. There's no math. Okay? Because the expected value of the mean squared for subjects is just subjects. There's nothing to divide by. There's no place we can do this. Right? So there's no error terms with the correct expected value of their mean square. So there's nothing we can divide by. So we can't, there's no F-test we can do. Also, who cares? What would our big revelation be if we found a significant effect between Justin and Arwen and Dave? That there is an effect of subjects. That different people are different. Ooh, call the Nobel people. That's not an interesting result. It's a boring, stupid, uninteresting result. It's also not something we're going to be able to generalize to any population. Really? Dave's different from Arwen. Well, look at us. Yes, no shit. I'm a 60-year-old man, and she clearly isn't. So, why is that interesting? That's not an interesting result. Who cares? So, the fact that there's no math to do it at first makes you go, ah, damn, maybe there's something there. Then you should realize, yeah, there's something there. People are different from each other. That's not a breakthrough. You are not getting a grant for that. You are not getting into graduate school for that. There's no publications coming for that. I have discovered that people are different from each other. Way to go. So it's also uninteresting. Right? Okay. So questions on that before we change gears a touch and talk about something that's incredibly similar to this. That's why it's talked about the same lecture. So you understand how this works. We lose degrees of freedom when we have the same subject, but it's usually worth it because we can make errors so much smaller. Okay. Repeated measures designs are actually special cases of randomized blocks. Okay? Kind of like how with a correlated or matched pairs t-test, when you think about that, we can use people, remember we talked about matching people up. They're the same people. We kind of treat them that way. It's the same sort of thing here. So, there's that t-test. You want to use the before and after, you use the same people, which is a special case of matching subjects. The ultimate matching variable is people, matching them up. You can match them up with other stuff. So the randomized block design, that in this case we get subjects that are matched on the dependent variable in this case. And I'll give you an example in a moment. You'll see why we do this and then how we attack it. Okay. All right, questions so far? Okay. So by extension, what we're doing here is we're going to do the same thing with repeated analysis of variance that we've done basically what the t-test did, which is what we're going to need is homogeneity of experimental units. In other words, which sounds like a weird way to put it, but we just want to make sure that if we have made a block up and the block is, well, here we have 3 people sitting right here. So the block is going to be Arwen and Madison and Jade. Okay, we have measured the 3 of you guys on something. I don't know what the thing is, but it's something where you all matched up. We better make sure you all matched up. You better be all the same. The math is going to depend on you guys all being the same. So let's match you up and make you the same, right? So when I say make you the same, what I mean by that is that let's measure that you're the same first. We're not going to. It's not something we do. And then what we have is homogeneity of experimental units. You're all experimental units, and you're homogeneous. Well, at least the variable we're interested in. And then we got another group. Got 3 folks back here. We can make them a group, or a block, we're going to call this, and you three guys can get a block. And the two of us are just left out. We suck. So, as long as we've done a good job measuring, and you guys are all the same, and you guys are all the same, and you guys are all the same, we're fine. There's a few ways we could do this. The obvious one is to let nature do it. If we had litter mates, like a litter of 3 is born, they're the same. Or twins are the same, except that there you can just do a t-test, right? Matched pairs, matched blocks. Now what I was talking about here was matched blocks. So the 3 of you would be the same on whatever variable we're interested in. The 3 of you are the same, and the 3 of you are the same. Okay? Okay. All right. So we're blocking on a variable, we're going to call it a nuisance variable. It's a nuisance because it's something we can measure and we know it gets in the way. Okay? So a nuisance variable is something that we can measure that will cause variation and we can remove it easily. Okay? So it would muddy the waters, basically, make it a little more difficult to find an effect if it was still there. So this is going to reduce error, which gives us greater power. So again, you can see the logic is very similar. In fact, it's the same as it is with repeated measures. And so the structural model is the same. It's going to be the one without the interaction, because we're going to get error because we have. Well, within this block, there's going to be differences. Within this block, there's differences. And within this block, there's going to be differences, individual differences. Okay? So, the model looks like this. That's the same model, eh? The difference is we don't have that interaction term anymore. We now have an error term. We have an error term because these aren't the same people. They're just 3 people in a block. They're just 3 people in a block. They're just 3 people in a block. They're not the same person. Any score equals the grand mean plus the treatment effect plus the block effect plus error, or residual. I'm just going to call that residual. You can call it error if you want. I'm just going to start using the word residual a little bit too, because you're going to start seeing it more and more. It means the same thing. It just means leftover. Residual, what's left over? And error really is just what's left over. Excuse me. Okay? Okay. Again, questions? Good. Okay, this is great. Well, some assumptions here. The sum of the treatment effects is 0. Duh. Yeah, of course it is. It always is. The sum of the block effects. Oh, that's weird. It looks like error. Yeah, because again, it's considered to be, or the effects of individuals if we're doing repeated measures. These are assumed to be random effect variables. Normal and independent would be of 0 and a variance of sigma squared sub pi and a variance of sigma squared sub epsilon. Error. Okay. Error is independent of pi. There's no interactions. There is no tau pi interaction. So remember before when I said, yeah, I'm different than Justin, who's different from Marwood, so we're going to be different in how we remember things. That is probably true, that this block here is different from this block here, is different from this block here, but we have no way of actually measuring that they're being affected differently, like an interaction basically, that kind of affected differently. So we can't measure it, so we're just going to have to assume there isn't one. We're going to have to assume there's no interaction here. Now, if there's an interaction, a tau by pi interaction, which we explicitly said there shouldn't be, that means error increases. Because there's the only place that the variance can go, the only place it can go according to the model is there. You'll lose power. The nice thing is your test becomes more conservative. It does not become more sort of liberal. It doesn't become more likely that you'll come up with a significant effect, so you won't make an idiot of yourself. But you might, say something's real that isn't, but you might miss something. You might miss something. So basically, don't have interactions. Because people say, well, how do you deal with this? Just don't have interactions. Now, that's not great advice, is it? But it's all we can do with this kind of design. Okay? It's up there with, hey doc, it hurts when I do this, and stop doing that. I mean, there's not a whole lot I can say here. Just don't have interactions. So I'm going to give you an example, because I think this is kind of might be hard to think about in the abstraction, but an abstraction rather. But I think it's easier to think about this as far as an example. And the example I'm going to use here are just a made-up study of different kinds of methods. Okay, these are method 1, method 2, method 3. Different methods of teaching. And these are going to be about language. Okay, this is the example I made up. Is about people learning to speak French. Okay, and the nice thing about this is, the reason I'm using this is we've got low, medium, and high levels of competence. That would be actually pretty easy to do, wouldn't it? Right? Because we could have low would be people that just did regular core French, right? Which is just the regular classes. And then medium might be something like French immersion. And high would be I went to French school. Okay? Not a French immersion school, a French school. There's a difference. And you notice that people who go to French school versus French immersion, there is a difference because you do some of your classes not in French immersion, and in French school, you do your courses in French because, of course you do. So I think it makes some sense that if we had 3 different methods of teaching French, that different methods might be affected by people's past experience knowing the language, right? That just follows, right? So method 1, let's say that's the flip. No, let's say it's just regular lecture. And method 2 will be the sort of flipped classroom they talk about, which is, you do stuff at home and then you sort of do a Q&A in the classroom. And the third one will, I don't know. Oh, the third one, their course is presented in an intensive format. So you do an entire university class in 3 weeks, that kind of thing. Okay. So like sometimes spring courses run twice as fast. They already run twice as fast, basically running 4 times as fast as a regular course. One thing we talked about here about 16 actually years ago was maybe moving to a plan like that, where you took one course at a time. You took a class for 3.5 weeks, then you took another class for 3.5 weeks. It's all you took all day. So you would take statistics with me for 3 weeks, and that would be all you would do, would be all I'd teach for 3 weeks. I thought it was a cool idea. A lot of people didn't. But that's a third method of teaching, method of setting things up. And again, I think we can see that depending on people's past experience, it's certainly possible that the teaching method would have some effect on, would also be affected, not only by the teaching method, but also affected by past experience with the language. So what we would do in this case is we would block on past experience. That's what this has done. Now, you might say, hey Dave, you said there can't be an interaction. There's an interaction there. Yeah, I know. The lines don't cross, but they aren't parallel. But they aren't, as long as it's not a disordinal interaction, I'm kind of okay. It's not disordinal. It's not ones with crossing lines. Once that starts, I think we got a problem. And you might ask me, well, what do we do in that case? What we do in that case is we don't analyze it using this kind of approach. Okay, so there's no fix we can put to allow us to use this kind of ANOVA if we have an interaction with our blocks and treatment effects. We just have to find another way of doing it. All right. So what you do is you look at your stuff in advance and you say, do I see the lines, if the line's not crossed, I'm probably in. We could do more than one repeated measures variable too, why not? Right? So I can think back, one of my honor students right now is doing her yes, her thesis is repeated measures. Yeah, Jamie's thesis is repeated measures. She has one group of people, they get tested in 6 different conditions. But it's actually, though the variables are different, it's a 2 by 3. What we have here is a 2 by 3 we got an implicit and explicit memory test. And we've got 5 minutes, 1 hour, and 24 hours. Those of you who are in my memory course know that implicit memory doesn't really decay in 24 hours. Explicit memory does, but implicit doesn't. So we should get a different decay function for explicit than implicit. That's called an interaction. But we're looking at forgetting. We probably want to test people over and over again. That's what we're doing. We probably want to test people in both implicit and explicit. So we're basically just using the same subjects. We're testing them both implicit and explicit memory, 5 minutes, 1 hour, and 24 hours. Okay? This is a standard, easy kind of research design that you would use in these kind of experiments. Okay. So what's the model there? Okay, I'm going to show you the model. This. So we got x equals mu, so that's obviously plus alpha and beta. We got implicit and explicit memory, so memory test type and retention interval. And then we got subjects. And notice how, again, this time we've exhausted the degrees of freedom. We don't have an error term here. We don't have at least a term called error. There's lots of error terms in here. There's lots of things we're going to divide by. We'll get the mean squared for something and divide by that. But it isn't, I mean, it's obvious to me what it is, because I know this already, but it may not be obvious to you. We'll get there in just a moment, and you'll see, oh, it is obvious to me. So what we have here is we've got, so it's be retention interval and memory test type, retention interval by memory test type, subjects by memory test type, subjects by retention interval, subjects by memory by test type by retention interval. Okay? All right. Very nice. Questions? Okay. So there it goes. I'm assuming 10 subjects per group. So how did I do this? There's an algorithm. There's an easy way to do this. And I'm going to basically over the next 3 weeks teach you a way of getting so you can always figure out what the error terms are every single time. And it's, like I said, it's an algorithm. There's a series of steps, and it's really easy. It's mechanical, but it involves practice. It's easy once you know how to do it. At first, it might look complicated, but believe me, once you've done it a few times, it's not that bad. It's you just got to practice. And the nice thing is anybody can make up examples, and you can trade them among your friends and that kind of thing. So the first thing you always list is subjects. Okay, at least at our point now, it gets more complicated. But right now, the first step we're doing, we're going to go subjects, and then we're going to talk about, we're going to bring in a variable. Let's say retention interval. It has, and let's not worry about the degrees of freedom over here yet. And then we cross retention interval by subjects. There it is. Now bring in memory test type. That's the M. I just used that because to remind myself what it is. So then we go memory by subjects, memory by retention interval, memory by subjects by retention interval. Are there any more variables? No, there are not. So now we have exhausted all the sources of variation. Now let's get the degrees of freedom. Subjects, so I just made up that there were 10 subjects. So there's 9 degrees of freedom for subjects. Remember, retention interval is easy too. It had 3 levels, so it's going to have 2 degrees of freedom. Well then, that's going to be 18, because it's 9 times 2. And then memory test type, there are 2 types of memory test, right? There is implicit and explicit. So it's going to have 1 degree of freedom. Subjects times memory Oh, it's going to be 1 times 9. It's going to be 9. And then this is going to be 1 times 2. It's going to be 2. And this is going to be 18. 1 times 2 times 9. Now, if we actually have exhausted the degrees of freedom, there shouldn't be any left. Well, let's see. How many degrees of freedom for total in our experiment? Well, there's 6 cells, and they each have 10 observations. So we have 60 observations. Therefore, we have 59 degrees of freedom. Let's add these up. 9 and 2 is 11, and 18 is 29, 30, 39, 40, 41, 51, and 8 is 59. We have 59 degrees of freedom. We did it right. The chance that you did it wrong and the arithmetic works is pretty slim. So it's a nice little check. Just do the arithmetic on the degrees of freedom. It allows you to make sure you did it right. Now, we have to then figure out, what do we test? Well, let's see. What do we test with what? We don't test subjects. Again, because it's not interesting and there is no mean square. It's just not interesting that we're all different people. Right? If we were all the same, I'd have to teach just one of you. Because then you'd all know it. It doesn't work like that. Subjects by retention interval. Well, 9 times 16. So we're going to test retention interval by subjects with retention interval. What I mean by that is we're going to take the mean square for retention interval and we're going to divide by the mean square for subjects by retention interval. We're going to test memory with memory by subjects. And we're going to test the interaction with the interaction times subjects. So what you do is you find the thing that you're interested in, retention interval, and then you look below it until you find the term that has the thing you're interested in and subjects. And if you've done this correctly, it's always below it. So the first part of this algorithm I'm teaching you, this algorithm was invented by Frank Yates, you know the guy, one of the ANOVA inventors. Not the racist one. So this is called Yates order. Yates's order, or Yates order. And what Frank Yates did, he came up with this idea of how you list things in an analysis variance summary table, then you won't make mistakes. So what you do is you go subjects, and then you take your variables, and you cross your variables with the ones above them. So look, subjects, retention interval, subjects by retention interval, memory by subjects, memory by retention interval. Some software still presents things in this order. Most of them don't anymore, which I don't like because it was great for teaching when they were always presented in that order. Okay, questions so far? Okay. So some conclusions about these designs, and then we'll maybe do another example. Repeated measures are used a lot. A lot of psychology is about change over time. And if you think of subjects as just another variable, just another factor, it's a random factor, but it's another factor, then it's easy to figure out the error terms, because as long as you follow Yates' order, you follow that set of rules, and I've given you basically one rule so far, there's like 5 or 6 of them, but they all sort of integrate together. It's really pretty easy. So figuring out error terms and components of a model like this, like I said, work because of Yates' order. It makes it easy, and it makes it so you don't make mistakes. One of the kinds of questions you're going to get on the final exam is you will be getting questions that have, here's the design. Tell me what the source of variation degrees of freedom are. Oh, here's a source of variation degrees of freedom table. Tell me the design. Right? In fact, about half the final exam is that. There's not just one question, there's one. Yeah. All right. So let's take a look, and let's play with an example a little bit here. Okay, so what I'll do, but first, before we do that, any questions on this? Okay, so think about this. You should be able to go, let's make this one go up. I'm going to draw here. Yeah, we got to kill that projector. Okay, so let's say we had a design that had, I don't know. First of all, we're going to end this because
That's